Hello, I'm Reuben Dorent, and I'm excited to present this joint work with Polina Golland and William Wells. In this paper, we introduce a new theoretical connection between the Jensen-Shannon and the Kullback-Leibler divergences that has direct implications for representation learning. In this work, we focus on maximizing the mutual information, which quantifies the amount of shared information between two random variables. Formally, the mutual information is defined as the divergence between their joint distribution and the product of their marginals. Maximizing mutual information plays a critical role in representation learning. For instance, to learn deep representations of data by maximizing the mutual information between data and their representations. Or in the information bottleneck framework, to learn a representation that only captures the information relevant for predicting another random variable. To maximize mutual information, we first need to be able to estimate it. Since mutual information is intractable in most real-world scenarios, several strategies have been proposed. The first family of methods relies on variational lower bounds. However, these approaches often suffer from instability, bias, and underperform in high mutual information regimes. Another family of methods takes a two-step approach. First, a discriminator is trained with a specific loss function, and then the mutual information is estimated from the trained discriminator. This two-step estimator can be very accurate, but they have a major drawback. They must be retrained every time the joint distribution changes. This makes them impractical for representation learning, where the deep representations themselves keep evolving during optimization. To overcome this limitation, a popular approach is Infomax, where the divergence is replaced by the Jensen-Shannon divergence, leading to the maximization of a Jensen-Shannon mutual information. Maximizing the Jensen-Shannon divergence via a variational lower bound is typically more stable since the Jensen-Shannon divergence is bounded and symmetric. To justify the use of this proxy for the true mutual information, Edge et al. Observed empirically that these two quantities correlate well. In this work, we go one step further and we provide a theoretical justification behind this empirical observation. We show that maximizing the Jensen-Shannon mutual information does increase a lower bound on the true mutual information. By analyzing the joint range between the Jensen-Shannon and the divergences, we demonstrated the existence of a new lower bound connecting the Jensen-Shannon and the divergences. This lower bound is optimal since equality is achieved for a family of probability distributions. Then, by restricting this general result to the mutual information setting, meaning by only comparing joint and product of marginal distributions, we obtain that maximizing the Jensen-Shannon information increases a lower bound on the true mutual information. Therefore, these results provide a theoretical justification for maximizing the Jensen-Shannon information as a proxy for mutual information. Then we demonstrated that maximizing the Jensen-Shannon information can be achieved by minimizing the cross-entropy of a discriminator that is trained to distinguish pairs of samples drawn either from the joint distribution or from the product of the marginals. Ultimately, we obtain an inequality chain that demonstrates that using such a discriminative approach maximizes a lower bound on mutual information. We validated our theoretical results through a series of experiments designed to assess both the tightness of our bound and its practical usefulness. We first analyzed this bound in a synthetic setting where both the mutual information and the Jensen-Shannon divergence can be computed exactly. And compared to other variational lower bounds, our bound provides estimate with reduced bias and variance. Finally, we demonstrated the practical value of our approach in the information bottleneck framework. When replacing the standard mutual information term with our discriminative lower bound, we achieved state-of-the-art performance on the MNIST dataset, improving generalization, adversarial robustness, and out-of-distribution detection. In conclusion, the main takeaway message is that if you want to maximize mutual information, our work provides a principled justification for using discriminative approaches. If you want to hear more about this work, please come by our poster. Thank you.